In biopharma, CE-SDS is our primary tool for detecting low molecular weight species or fragments. To separate proteins by size using CE-SDS, we have to denature the sample first. Unlike SEC, which is a physical filter, CE-SDS uses an electric field to pull molecules through a gel-like matrix. Without SDS, proteins would migrate at different speeds based on their unique native charges and 3D folding, making it impossible to accurately determine their size. We use SDS as the great equalizer to remove those variables. First, it acts as a detergent to denature protein, unfolding those complex 3D structures into simple linear chains. Then, it coats the polypeptide at a constant ratio of about 1.4 grams of SDS per gram of protein. This masks the protein's original charge with a uniform blanket of negative ions. The result is that every protein now has the same charge-to-mass ratio, meaning they all feel the same proportional tug from the electric field. This ensures that as they move through the sieving matrix, their migration is determined solely by molecular weight, giving us the highly reproducible purity data we need for CMC and clinical release. Now, if we just pull these proteins through an open tube, they would all move at the same speed. To separate them, we fill the tube with a polymer sieve. This acts like a molecular obstacle course. When we apply high voltage, small proteins navigate through the sieve quickly, while large proteins get entangled and come out last. As the proteins pass a detection window, a UV light reads them. This produces an electropherogram. The x-axis shows migration time, which tells us the molecular weight, and the y-axis shows signal intensity, which tells us how much of that protein is present. Taller peaks mean higher abundance. Samples can be analyzed by CE-SDS in two ways. Reduce protocol uses chemicals to break disulfide bonds that hold the molecule together. Non-reduced protocol keeps the antibody intact. Alkylating agent is used to lock the disulfide bonds in place, protecting them from shuffling or breaking during the heat of sample preparation. By utilizing both these protocols, we construct a comprehensive analytical picture. The reduced method validates that we have the correct parts, while the non-reduced method confirms they are assembled into the correct, stable therapeutic product. The primary goal in CE-SDS optimization is to minimize artificial fragmentation during sample preparation for both methods. While we aim for a complete reduction in the reduced protocol, the non-reduced protocol requires a careful balance of complete cysteine capping to prevent disulfide scrambling. This slide summarizes the critical parameters you should tailor to your specific molecule, ranging from reagent concentration to precise heating times, to mitigate these primary failure risks. These values listed here are commonly utilized for monoclonal antibodies. When refining CE parameters, we have to balance resolution against sensitivity. If we're struggling with peak overlap or broad peaks and need better resolution, our first move is to decrease the injection time while keeping the voltage constant to sharpen that sample plug. On the flip side, if we need a stronger signal to catch low-level impurities, we can increase the injection time in 5-second increments, but we must keep a hard cap at 40 seconds to avoid overloading the capillary. Whatever we do, we must remember the golden rule. Do not push the voltage above default levels. Higher voltage induces joule heating, which leads to catastrophic bubble formation and will kill the run instantly. Separation time is another piece we need to optimize for an unknown molecule. Always start with a 23-minute baseline and tune this iteratively, increasing the run by 2 to 3 minutes at a time until every target peak is clearly detected. Once we've found that ideal migration time, we strictly add a 2-minute buffer to the end of the method. That extra padding is essential to absorb any minor injection variability and ensure our data remains consistent across the entire sequence. In summary, SDS equalizes a charge. Controlled heat prevents fragmentation. IAM shields non-reduced samples. And injection time, not voltage, is your best lever for optimizing resolution. Keep these in mind, and your CE-SDS data will stay clean and consistent.